dark matter searches and how liquid xenon plays an important role in the searches, although we changed your title, I just noticed. Okay. So,
it might change again, I don't know.
all right. So Aaron started out in University of Florida. He worked there with Laura Bottas,
Okay.
right? And then the original xenon experiment was Xenon 10. Then he had a stint in Zurich, where he worked on the Cherenkov telescope array, which is the next generation of air Cherenkov telescopes, which is going to be somewhere in Africa, is being planned. And then now he's here in Davis, working on LUX and LZ. There.
Thank you. Okay, so a little disclaimer at the beginning. This is supposed to be more of a seminar, or sorry, a colloquium talk, and this is the particle seminar. So it's going to start off slow a little bit, and so it'll get more interesting, I promise. But I have to tell a little bit of a story for a colloquium, and if I'm going to tell you the story about LUX and LZ, I have to tell you the story of dark matter. So I'll show you something that you've probably seen. This is from an obscure movie from the 70s. You see Obi-Wan is telling Luke Skywalker about dark matter. He says it surrounds us and penetrates us. It binds the galaxy together. Well, he might as well have been talking about dark matter. And I don't know if George Lucas in 1977 knew about dark matter. It's not far-fetched because we knew about it at that time. But actually the story of dark matter starts a long time ago, much earlier than 1977, in a galaxy far, far away. Okay. So if you think back to the 1920s, we learned something very profound, and that is that there are a lot of galaxies out there besides our Milky Way that are similar in size and sometimes larger. The universe is much bigger than we thought. And we learned more things that are fundamental about it, about galaxies and whatnot. Hubble was one of the pioneers of this. Number one is we discovered that the universe is expanding. We also learned that galaxies they're not just scattered randomly throughout the cosmos. They tend to be clustered in groups that we call galaxy clusters. This is a picture of the Coma cluster. It's one of the earliest galaxy clusters that was studied. And maybe it's tough to see because there's a lot of black in the screen. But okay, so there's some foreground stars that you see, but all of these little fuzzy dots are galaxies, part of the Coma cluster. And there was a Swiss-American astronomer in the early 30s who was studying this cluster. Remember, this is only about a decade after we discovered that there were galaxies outside of our own. He was studying this cluster, and he asked a pretty simple question, which is how do you estimate the mass of a galaxy cluster? Well, one way you can do it is that we know how bright the sun is and how massive the sun is. So you can look at the brightness of all these galaxies, okay, and use the brightness as a proxy for the number of stars, and the number of stars as a proxy for the mass of the galaxies. But also, we have the Doppler effect, so we can measure the line of sight velocity of these galaxies. So we can measure the velocities that they're traveling also with respect to each other. And then you can use the virial theorem, which is really powerful to tell you. It gives you a relationship between the kinetic energy of an object and the potential that it's in. So there's basically two different ways that you can estimate the mass of this collection of galaxies. And you don't expect equality and complete agreement between these two techniques, but Zwicky came up with a discrepancy of about a factor of 400, which is, he couldn't explain it. He proposed that, you could understand this if there was something called dunkle materia, which is dark matter in German. And it didn't really catch on. Nobody really paid much attention to this. I'm told that this picture is a pretty good description of his personality. And it could be that maybe he was antagonistic to his cohorts, and they didn't pay attention to him that way. But it was a really interesting thing that he learned really early on, shortly after we even discovered that there were other galaxies in the universe. Okay, so that's one anomaly. All discoveries start with anomalies. So let's move forward to the 1960s and 70s. People were trying to scrutinize galaxies more, and they asked, let's measure the mass of a galaxy. Vera Rubin is an American astronomer. She wasn't the first to do this, but she was the first to note how important this technique is. She said, if I take a spiral galaxy edge on, I can use the Doppler shift again, the Doppler effect again, to measure the tangential component of velocities as they're spiraling, of these stars as they're spiraling around the galaxy. And we know something about how bright the center is. Most of the stars are concentrated in the bulge. There's sort of an exponential fall off in density of stars as you go along the disk. And if that's dominating the mass of the galaxy, we can predict how the velocity, the rotational velocity of stars behaves as you move away from the center. And you expect this sort of falling curve like this. This is radius in the center, this is the tangential velocity. But you measure, for one galaxy, you find that you don't get agreement with that. You get sort of flat, it's called a rotation curve. You go for more and more galaxies, you start to see that there's a pretty big problem here. None of the galaxies behave as though the dynamics are being dominated by the stars in the disk. And so this is another piece of evidence on a much smaller scale than galaxy clusters, and the scale of galaxies, that there may be some additional matter that we can't see. You can explain this discrepancy by introducing another component of the galaxy that adds to the mass. Okay. So that's some scale of galaxies. And I'm just touching on the story of dark matter. I'm just touching on highlighting a few chapters in this story, because, of course, if I was to tell the whole story, there wouldn't be time. So I'm just going to tell you one more thing, and this is probably my favorite astronomical picture. And it's a picture of the aftermath of interacting galaxy clusters. This is known as the bullet cluster. There's actually two galaxy clusters that sort of collided in their own way about 150 million years ago. Now, if you look at a galaxy cluster, of course there are stars, there are galaxies, but the dominant baryonic matter is in the form of this hot intercluster plasma. It's the hot hydrogen that permeates between galaxies. And you can see it in X-ray. It's so hot that it emits X-rays. And what happened with these galaxy clusters, they sort of pass through one another. Okay. These researchers, what they did is they said, okay, let's look at where is the intercluster plasma. So they looked in the XMM, I think it was the XMM satellite, it's an X-ray telescope. Oh, was it Chandra? Okay, that's good. And you can map out here in pink where the baryons are, essentially these galaxy clusters. And so then you can also ask, okay, where's the most of the mass in the galaxy clusters? By using gravitational lensing. And that's what they've shown by shading these blue regions. And so the pink represents the majority, by far, the majority of baryons in the cluster. And if that was what was dominating the mass of the clusters, then certainly the center of mass of these clusters would be where you see the pink, but indeed it's separated. And so the interpretation that we have of this phenomenon is that there were these two clusters, mostly dark matter, also some intercluster plasma, also galaxies. They sort of collided. The dark matter is non-collisional. It went through each other. The two blobs of dark matter went through each other, but the two clouds of intercluster plasma collided. And in fact, you can even see the bow shock here in the smaller of the two galaxy clusters that is a result of that collision. And this is a unique example of evidence for dark matter, because a lot of the other pieces of evidence of dark matter we have are anomalies regarding the strength of gravity. But this is actually a lateral displacement of matter and center of mass. So this is really sort of a smoking gun piece of evidence for dark matter. Okay, so those are the highlights I'm going to tell you about in terms of the story of dark matter. I'm just going to summarize right now that the picture that we have. So we have roughly, that dark matter makes up roughly a quarter of the energy budget of the universe. I'm not going to talk about dark energy, that's most of it. We know that dark matter was produced cold, that means it was non-relativistic when it was produced. We know it has to be cold, otherwise it couldn't have formed structures, structure growth that we see here. We know it doesn't clump on small scales. One of the first ideas for dark matter was that it was made up of Jupiter-sized objects that don't emit light. But you can do tests for that with microlensing, and found that that's actually not, you don't see any evidence of objects like that could account for it. We know it played an important role in the early universe. You can see this cosmic microwave background, and also in the formation of structures. And what will become important in a few slides is that we also know something about the dark matter in our neighborhood, in this room, what its density is and what the velocities of dark matter are. So, okay, we don't know what it is. So what is the dark matter? Well, we know it's not anything that can be explained by the standard model. One of the ideas early on is that it could have been neutrinos, but that's a debunked theory. And there are many ideas about what dark matter could be. I'm going to focus on one for right now, and has a really awe-inspiring name, the WIMP Miracle. So it's a very generic idea for how you can produce dark matter. In the early universe, for any given particle, it was being produced by collisions. It was also being annihilated with collisions with similar particles. And these rates of production and annihilation would have had to balance in equilibrium. But as time goes on, the universe cools down, as the temperature drops below the mass of the particle, the production mechanism drops off. At the same time, the universe is expanding, so the annihilation mechanism, it's becoming harder and harder for these two particles to find each other and annihilate. So the annihilation mechanism shuts off. And if conditions are right, this is a curve. Basically, time is going here to the right. This is the number density, essentially. Here's the solid curve represents what thermal equilibrium would be for a particular particle species. But if these conditions are right, what can happen is that the production mechanism and the annihilation mechanism shut off essentially simultaneously, and we're left with a relic abundance of these particles. They're too sparse to find each other to annihilate, and the temperature of the universe is too low to produce them anymore, so we're left with these as a thermal relic, we say, of the Big Bang. And the actual abundance depends mainly on what its actual annihilation cross-section was. And this is really interesting because there's no resort to ultraviolet physics. There's basically no fine-tuning required. It's called the WIMP Miracle because when people do this calculation, they notice that if I put cross-sections here, characteristic of the weak scale, you basically get the right relic density out. This is really interesting. This is something from microscopic, high-energy particle physics telling us something about the cosmos at large. And so that's why it's the WIMP Miracle. This is if you put in something that's characteristic of the universe that we know today, you get something that you see on large scales. And we call these particles weakly interacting massive particles. And it's really been something that people have sort of been in love with for a while. The paper where this calculation was first made came out in 1977. I guess it happens to be the same year as Star Wars. And this is such a nice idea that you can even say that as physicists we've sort of been, in Facebook language, been in relationship with WIMPs since that time. And this has really guided a lot of our efforts theoretically and experimentally. So if you want to detect this thing, you have to exploit how this particle could couple or interact with standard model particles. And there's several ways you can do that. If you think of time going to the right here, I can try to produce it with standard model collisions, colliders. If I rotate this diagram the other way, in regions of the universe where there is high density of dark matter, like the center of the galaxy or whatnot, you can try to have annihilation of dark matter particles that produce standard model particles. If I rotate this diagram again, I can get a dark matter particle scattering with a standard model particle. And people are actively pursuing these three techniques, and each three technique has its own set of strengths and weaknesses, but we're going to be talking about direct detection, so scattering of dark matter particles with standard model particles. So if we want to know what to make of this and how to proceed, we have to know something about our local environment. It's the dark matter like in this room or in a lab on Earth where you can do it. So we know that the local density of dark matter is about 1/3 of a proton mass per cubic centimeter. We have some idea about the velocities. This is about 1,000th the speed of light. It's the characteristic velocities of them. And we know that they have probably something similar to a Maxwell-Boltzmann distribution. There's a lot of work in astronomy of people trying to do simulations to figure out what some more precise numbers and characteristics for these local parameters, but have an idea of roughly what they could be. And so if you plug that in and ask, okay, what would happen if one of these particles were to interact with normal matter? Mainly what you would see for large class of models are nuclear recoils of order 10 keV. So something would come in, kick a nucleus of an atom, imparting about 10 keV of kinetic energy to that nucleus. So if I wanted to detect that, I have a rather difficult task because 10 keV is not a lot of energy, and this is a very rare process. So one of the things I can do at the start is that, well, it's not the case that every type of nucleus is going to see the same rate. Maybe some nuclei look bigger to a WIMP than other nuclei. So I would like to choose a nucleus that presents a really large cross-section to a WIMP. Okay. I also want to do it, try to detect it with the material that I can use in a particle detector that's going to be able to detect a few keV nuclear recoils. And because this is a very rare process, such a particle detector might also see a lot of other types of signals from backgrounds, from residual radioactivity and detector materials. So I want to do something where I can actually build an ultra-low background detector. So I'll explain what I mean by that. So when energy is deposited in the material, it generally is deposited in 3 channels. I can produce ionization, kick out electrons, atomic electrons. I can produce scintillation, that happens when electrons fall back from atoms. It also produces heat, thermal, vibration. Okay. And it's important to note these different types of channels where energy can go because it helps me understand how I can distinguish between different types of interactions in the detector. So what I've shown here are a selection of some direct detection experiments. And their position on this triangle indicates what types of signals they detect. So for example, crest detects scintillation and heat. Okay? And these ones detect scintillation and ionization. And then the color, I sort of color-coded them to tell you what type of atom, what elements are these detectors using. Some of them are mixed targets, and some of them are pure, for example, xenon, or argon, or germanium. So let's take a look at what we would expect to see with some of these elements. Okay, so we're looking for this type of interaction. Some dark matter particle comes and smacks the nucleus. In this interaction, we don't really know what might happen there. This thermal production of dark matter is sort of agnostic about the ultraviolet details about what happens in that vertex. But there can be any number of effective interactions here. And one of the simplest ones is that there's a spin-independent interaction where this dark matter particle essentially couples equally to all nucleons in the nucleus. And if that happens, then the cross-section for this interaction is going to scale like the square of the number of nucleons. And so a large nucleus like xenon is going to have a much, much larger cross-section than something like germanium or argon. And this is a picture of the expected interaction rate as a function of recoil energy that you would see for the same WIMP in these 3 different nuclei. And so, of course, in red is the one that jumps out at you. See how much larger of an interaction rate that you would see in xenon with respect to germanium. Okay, so from this node, and maybe Amelia would disagree, you might want to pursue xenon as a detection mechanism. And in fact, people have.
Are you going to provoke the people like that? That's good.
So why isn't everybody doing xenon? Is it too expensive, or
It is expensive.
can you make it bigger than if you do
So germanium does have the disadvantage that it's very difficult to scale to large size. I was going to explain something about scalability. That's a really important thing. There's some other notions, and so I probably can't say anything about argon without offending Amelia.
But you should. Yeah, go.
But that was for a 50 GeV WIMP. The WIMP is 1 GeV.
Right.
Germanium is better.
Okay.
Well, not necessarily, because this would still be higher for a 1 GeV.
Yeah.
But you notice
Threshold.
exactly. You notice that this you get an advantage from xenon only if you can push the threshold very low. And in germanium, you can push the threshold probably a bit lower than in xenon. So this signal changes depending on the mass of the room. There's another thing that I'll discuss in a second, which gives some advantage to liquid argon. We'll discuss it now. Okay, so if we want to build a detector out of xenon to search for this stuff, there's different ways you can think of to do that. But there is one technology that's been has made a really big impact in the field, and that's the dual-phase time projection chamber. I just show sort of a cartoon here. Basically, you have a tank of liquid xenon, and you have some grid electrodes that you put in place to apply electric fields. You have some photomultiplier tubes, the top and bottom. Okay. And there's an important part here, and I'll come back to that. There's the liquid level. It is dual phase. I said liquid xenon before. This is dual phase, so there's the gas part is important. So if there's energy deposited by some incoming particle, okay, that's going to produce scintillation photons and electrons. And the scintillation photons will propagate. They will be detected by the photomultiplier tubes. The electrons see this field, and they are going to drift up to the surface, where they're extracted from the surface and then are accelerated through the gas. And as they accelerate through the gas, they hit xenon atoms and produce more scintillation photons. And these scintillation photons are also detected by the photomultiplier tubes. Okay. Now, you're probably wondering why we go through make such a complicated device up here to extract electrons and convert them into photons. And it doesn't make sense unless you realize that, well, reading out the electrons in this way is one of the most sensitive techniques that we have available to us. And it makes us sensitive to ionization signals as small as a single electron. You can actually see single electrons discretely popping up through the gas that way. So that's important. I'll come back to that later in the talk. There's another thing is that I said that we're interested in looking for nuclear recoils of over 10 keV. And most of your background is going to be in the form of electronic recoils from gamma rays, for example, or beta decays inside here. And so if you can distinguish which events came from nuclear recoils and which events came from electronic recoils, you can beat down a lot of your background. And this is, for example, in liquid argon, they have another handle dealing with the quantum simulation that helps them distinguish between electronic recoils and nuclear recoils. And in liquid xenon, we do that particle ID essentially by looking at the ratio of the ionization to the scintillation level on an event-by-event basis. And again, something we talked about before, which is this type of design, it really lends itself to scalability. I can build a very large detector, and if I have some residual radioactive isotopes in the materials of my detector, the outer layers of xenon can shield those particles from entering the inner layers. And that only really is beneficial if I can build a very large detector. So something like small, like a germanium detector, like the CMS detectors, which are the size of a hockey puck, can't really enjoy that feature that we have. And just to give you an idea about how powerful this technology is, the first time a liquid Xenon TPC made any dark matter results was in the middle of 2007. And the first time that a liquid Xenon TPC made the best dark matter search results for WIMPs was 6 months later. So the time from the introduction of this technology in the field to the time that it was leaving the field was 6 months. So that gives you an idea about how powerful and how fast-paced this technology is. And ever since then, it's led the field. So this is a really, really powerful technique for particle detection and measuring dark matter.
When you say vast, right? Is it vast across, I'm just trying to.
Right,
Is it vast across the field, or
it would be best, so
can it do spin dependent and spin independent and all these things, or are there other methods?
that's right, so there's some subtleties. For spin independent, it's the best for a wide range of masses. And then for spin dependent interactions, you generally can't make the same assumption that you do for spin independent interactions that the WIMP interacts with all nuclei, because there's generally going to be some difference between protons and neutrons and other couples. So for coupling to neutrons, it has the best sensitivity. There's some big uncertainty about how it couples to how WIMPs could couple to protons in xenon, because all the nuclei with spin in xenon, naturally occurring xenon, are nuclei with odd neutrons. The spin of the nucleon, the spin of the nucleus is carried mostly by an unpaired neutron. So the coupling to protons is sort of just a residual.
Be careful when you say vast.
That's right. Yeah. But even with the proton couplings, it's still very much competitive with other nuclei that have proton docking. So there's a bit of a timeline of dark matter detectors that are dual phase Xenon TPCs, and currently the most up-to-date one is the large underground Xenon experiment, which is called LUX. And we here in Davis Monty was one of the founding members of this collaboration. This is a photo taken when the detector was being assembled, looking from below upwards. So if we take a look at here, basically this whole bottom section is removed. Of course, there's no liquid xenon inside, and the photo is looking upwards. And if you squint, I'm not sure if you can see it here, you can see the grid wires on the bottom. Here are the photomultiplier tubes on top, and there's a series of grids here and here where the liquid level would lie somewhere inside here. And all the white stuff that you see surrounding is Teflon. There's some technical details I don't think I need to really go over, just to give you an idea of scale. This is about 0.5 meter in diameter, about 0.5 meter tall. And that size of xenon is about 250 kilograms. All right, so this game is something where we look for very rare events. And so we have to try to reduce the background as much as possible, as I mentioned. And so we put this detector, once it's buttoned up, it looks like this. We put it inside a large, about 300-ton ultra-pure active water shield. These are photomultiplier tubes that live inside the water. It's full. And that can look for things like cosmic muons that will pass through the water tank and produce backgrounds that way. And then, more importantly, the whole thing lives a mile underground in South Dakota in the Sanford Underground Research Facility. So this is sort of a schematic picture of the way that the lab looks. This cavern here is where LUX lives, and this was dug in the 60s, and this is where solar neutrinos were first discovered. And it's in the same cavern that we operate LUX. And we put it underground because the cosmic muon rate that we would see here is a factor of about 10 million less than it would be at the surface. So it's another thing that we do to reduce backgrounds. So this is giving you an idea of the makeup of the collaboration and also the conditions outside that we experience when we go on site to do shifts. This was March of last year, collaboration meeting. So look, here's Monty, and then in front of Monty there's a Yeti. So this is actually, believe it or not, this is actually the official, collaboration official corporate photo, and somebody put a Yeti inside. But the rest is not Photoshop. That's actually the way that the sky looked. And I think Serge is there. All right, so maybe dive into a little bit of technical details. I said that you can do identification of the incoming particle or the interaction type based on the ratio of the simulation, or the ratio of the ionization signal to the simulation signal on an event-by-event basis. So these are some calibration data. And this vertical axis is the same for both plots. This is basically the ratio of the ionization to simulation. And if you were to see these two calibration data sets are overlapped on top of each other, these are electronic recoils, these are nuclear recoils, you would see that they are, in fact, separated vertically. It's basically this parameter space that we use to distinguish if a particle is something that hit a nucleus or something that hit an electron. These are calibrations, this is not WIMP data. So what we can do, though, is use those calibrations to tell us about the identity of the events that we see when we take science data. This was our first results, 85 live days and about 100 kilograms, 118 kilograms of fiducial mass. The blue curve, this section here, this band, is where we would expect electronic recoils or backgrounds to lie. And the red band is where we would expect nuclear recoils to lie, or signal. And so these events that we collected in these 85 days are very consistent with our background model. In fact, profile likelihood test shows that we have about a 35% consistency with our background model of electronic recoils. So it's a null result. Not so exciting, but it is still important. And just to give you an idea, we're just talking about spin-independent or spin-dependent interactions. If I assume that I have spin-independent interactions, I can interpret this null result in terms of excluding regions of parameter spaces, the WIMP nucleon cross-section versus WIMP mass. This is sort of canonical parameter space in direct detection experiments. There's some other exclusion curves that have been set by other experiments, and the LUX result, which is LUX 2013 is actually published in 2014. And then here's some 30 blogs that came out recently. And so when I say it's the best in the world, really I mean that we've carved out the most amount of parameter space. Let's say this interpretation. And there's an interesting feature, and that is this: the bottom of this curve is at 760 yoctobarns cross section. We've excluded down to 760 yoctobarns, and I wasn't really clear. I mean, I remember things like what is nano, what is pico, what is femto, and I actually had to look up what was 10 to the minus 46 square centimeters in barns, and yoctobarn. Yocto is the smallest scientific prefix that exists. It isn't anything lower. So after this was an 85-day exposure. We're continuing data for 300 days, projecting 5 times more improvement. In the future, the next version of this experiment would be the LUX-ZEPLIN experiment. We're projecting about a factor of 1,000 improvement on top of that. We'll be below a yoctobarn, and we're going to have a big problem because we won't have a prefix for that. We're going to make one up.
Hella small.
What's that?
Hella small.
Hella small. Hella small barn. Maybe not a barn. So this is the exciting news that came out recently. The funding agencies in the U.S. have had a sort of contest for the sort of next generation of dark matter direct detection experiments. They wanted to put a bottleneck in the field because as the experiments go on generation, they get bigger and more expensive. And instead of having a whole field of experiments, they said, look, we want to dump a lot of money into a few experiments. And so there was a down selection by the funding agencies. And afterwards, 3 experiments were selected: LUX-ZEPLIN, which is the successor to LUX, and then CDMS, or Super CDMS, which is a germanium detector. And I'll show a slide in a few that'll show you the differences in terms of sensitivity. And then a third one was chosen, which was the ADMX experiment. It's an axion dark matter search. I didn't say anything about axion. It's another dark matter candidate. It's not the WIMP. That's something else. And so those 3 experiments were selected. So this is now a bona fide DOE project now. And it will go into the same water shield where LUX currently is. It's going to get some cool new features, like it's going to get, this green thing is going to be a liquid scintillator veto. It's going to be quite a bit bigger. The fiducial mass is going to be over 5 tons of liquid xenon, and that's slated to begin construction in 2017. Actually, that depends on whom you ask, this date, because it depends on the funding profile and everything else. Okay. Now, to give you an idea of where we're looking for the sort of main science goals of LZ, this is a really, really busy slide that was produced by a group called Snowmass. And here is, let's see, I think this is current LUX, or maybe this was produced before LUX was first, the first results came out. The projected sensitivity of LZ is down here. Things like super CDMS, you see at low masses, all these detector technologies start to lose sensitivity, but super CDMS is projecting some very, very competitive sensitivities to these very low mass dark matter candidates that they can do there. There's an interesting feature of this plot, and that is that at some point we have a big flux of neutrinos coming from the sun. There's a diffuse supernova set of neutrinos, atmospheric neutrinos, and these neutrinos we think, can scatter with nuclei. And this is an irreducible background. We can't shield our detector from neutrinos. And so events that come from neutrino scattering on nuclei are going to look a lot like events of dark matter particles scattering on nuclei. And so this produces a very hard floor. It's a little bit different for each type of target nucleus, but essentially it's a hard floor for any given experiment of how far can we probe this WIMP hypothesis. And so it essentially doesn't make sense from an experimental side to probe, to ask questions about WIMP models that occur below here. There's also there's a softer floor, and that is that all these neutrinos can also interact with the electrons in the atoms. And that produces a soft floor because you can reject a lot of those. All right, so this is, you could probably stare at this plot for hours. We're not going to do that. But it covers many decades, and which is really interesting because let's step back for a second and look how the field of WIMP-direct detection has progressed over the years. So there's a website called DM Tools. It's been around in the field for a long time. It basically is a collection of all the different dark matter exclusion limits historically. And the earliest ones you can find in there are from the year 2000. Okay, so we'll start there. This is shortly before I got involved in dark matter detection. So I've gone through DM Tools, and for each year from 2000 until about 2013, picked the contemporary data, both experimental exclusion limits, this was DAMA, if you know about that, and theoretical predictions. Okay, so there's 2000, there's 2001, and I want to give you a sense of how the field has progressed over the years. Okay, we started out up here, we progressed down here. It's about 4.5 orders of magnitude in this case 13 years of running. There would be a 2014 plot which would have the same LUX plot that would have also dark side that I didn't get a chance to make. It's pretty impressive, 4.5 orders of magnitude improvement in that time. Did you notice anything else?
The theory is still sliding
That's
away.
right.
It's going down.
Yeah, so the experimental limits are going down, and so are the theory projections. Now, of course, that's a bit unfair because the theorists, of course, use evolving constraints from experiments. So of course, they're not going to predict something that's up here. But it does give you a sense, if you've been in this field for a while, that from an experimentalist point of view, that you're sort of chasing after the target. Maybe that's unfair. I don't know. So from a theorist perspective, I was trying to think about what what it might be from a theorist perspective. Maybe like a bag in minesweeper. You can stake your entire career on some of these. In fact, some theorists stake their entire career on many different types of things. But maybe I'm giving you a sense that there is maybe a bit of discomfort growing in the field. I said as an experimentalist, we feel like we're chasing a moving target. Theorists maybe have no idea at this point what to look for. And you can ask, why is there discomfort? And, well, we can ask, okay, let's think back to the WIMP Miracle that we had, this idea of how we could produce dark matter in the early universe. And we said it was a miracle because if we plugged in weak scale annihilation cross sections, we get the right Orelic abundance. So what's weak? Well, weak is Z exchange. But if dark matter could interact with normal matter with Z exchange, you'd have cross sections up here. It's been excluded a long time ago. What's the next thing? You could have Higgs exchange. Okay. These are intentionally fuzzy lines here, but Higgs exchange, that's basically what's dominating here, is something that we're probing as well. Now, there could be other things like, if you're a fan of supersymmetry, you have Spork exchange, or other things. But essentially, if dark matter exchanges or interacts with normal matter by exchanging Higgs, this is sort of the lower end of where the cross section can be. We're starting to carve out a really big portion of that space. Okay. So another thing you can ask is, yeah.
Does that assume that annihilation cross-section is related to the
Oh, this is basically, okay, annihilation cross-section. Well, there kind of has to be a relation because in order for thermal equilibrium to be set up in the early universe, there has to be some coupling between the standard model and these particles.
Sure, but
It's crossing sync.
okay. So you assume because in some other models you don't have to assume that say dark matter scattering cross section does not need to be coming from the same principles than say annihilation cross section.
That's right. I have some slides on that. But this is sort of general natural arguments about, and this is just asking about just the scattering. Okay, I mean we know what the nuclear charge of a nucleus is in terms of Z, what the coupling to Z is, what it would be for neutrino, and so same thing with the Higgs. And so you can make some sort of hand wavy, get a sort of order of the idea of the scale of the cross sections that we would see if Higgs are being exchanged or if Z's were being exchanged. Okay, there's another thing you can do. And that is, if I have some physics beyond the standard model, I can write down some important parameters of the standard model as a function of the parameters of this new physics. Okay? So for example, I can write down the mass of the Z boson as a function of what I'm going to call P sub I. Actually, I'm not calling it, this is from the paper. Which are the parameters of some other model. Okay? Now, however many P sub I have, I have to constrain them so that they don't screw up the standard model quantities that I have. They also don't screw up the relic abundance. And so the constraints I have from current constraints or current experimental results will confine my allowed P sub I to some manifold in some large dimensional space. But then I can ask, okay, let's take a look at, again, the mass of the Z. Okay, for any given point in space that's allowed, I can ask, okay, what's the derivative of the Z mass as a function of that parameter? I can turn that into a dimensionless number, add them in quadrature, and this will give me an idea of how finely tuned that point in parameter space is. Because at that point in the parameter space, the Z mass changes a lot when I change that parameter a little bit, and that's true for many different parameters. Then the result of this is going to be a large number. And it means that that parameter had to be selected very carefully in order to get the correct Z mass to come out. So there was a paper that came out last year, and they took a particular flavor of MSSM. This is the pMSSM. It's a little bit less constrained than CMSSM if you're an MSSM aficionado. And for they scanned parameter space and sort of restricted it to regions that were allowed by clutter constraints and also astronomical constraints. And for every point in parameter space, they can calculate what's the mass of the dark matter candidate. Gives you a point here. They can ask what's the cross section, the spin independent cross section. And then it can also calculate this delta total, this fine-tuning parameter. And, okay, they had to sort of split off the Higgs mass parameter mu to plus and minus. And these guys are actually, one of them is a member of the Xenon 100 collaboration, which is another Xenon dark matter research. Higgs Xenon parameter, sorry. And so here was Xenon 100, the first results, Xenon 100, the most recent results. Anything Xenon 1 ton, which is going to be sort of in between the scale of LUX and the LZ. We'll have a sensitivity down here. And you see that we're starting already to leave these regions of parameter space where you don't really require a lot of fine-tuning. You're starting to have to invoke some fine-tuning of parameters to get a viable WIMP. It's less strong an argument in the negative mu case, but it's still there. And that's a bit untenable because remember, one of the ideas of the WIMP Miracle is that it was a candidate that required basically no fine-tuning. And
So when you say the bottom plot is suggesting that naturalness says that WIMP is low mass?
But that could be the case. That's right. That's what they say in the paper. They say that if you are persuaded by naturalness arguments, you sort of have to not care about this region here. But it's taking what seemed to be a very broad field, and we're starting to see that maybe it's not quite so. The WIMP is not quite so natural that we thought. It's still a very interesting, well-motivated candidate, but it's less so than we thought originally. And so if we go back to our Facebook language here, I'd said that we've really been motivated by the WIMP Miracle for a long time. I'd say that physics has been in relationship with WIMPs for that time, but maybe it's getting a bit complicated. I'm not sure that we're really ready to say goodbye to WIMPs, but it's certainly it's not what we thought it could be. And we know what happens when a relationship gets complicated. We start to look at other possibilities, other options. And in particular, one thing you might ask is, well, here's again our sort of canonical direct detection exclusion space, mass, cross section. And we've sort of just been pushing down here. You can maybe ask, well, what might be over here? And this sort of vibes a lot with the new Fermilab and DOE terminology of instead of pursuing the energy frontier, you pursue the intensity frontier. If you go towards, you want to look at colliders, for example, for these low mass.
But don't you need dark matter to be cold for galaxy formation?
That's right. So the constraints on thermal freeze-out for dark matter to be cold, actually, here's, just to give a sense of scale, here's 1 GeV, here's 1 MeV. The constraints are actually at the KeV scale for that. So the constraints in the temperature of the dark matter mean that it has to be more than a few tens of keV. So even here at the MeV scale, we're fine.
Oh, I thought it would be hundreds of GeV.
No, it's there's a really weak dependence on the mass actually. It's logarithmic.
So that would be hot dark matter, wouldn't it?
KeV scale, no, it could still be cold.
Meaning,
If it's a thermal freeze-out relevant.
meaning non-relativistic.
I mean non-relativistic when it goes out.
So basically temperature less than mass or older mass is still not relativistic.
Yes. The freeze-out temperature also depends on the mass as well.
Kinetic energy. Good.
That's right, yeah. It's not that the freeze-out temperature is a fixed quantity. It depends on the.
So it's a soft
That's right.
turn on. There are no other constraints, I guess.
Well, I mean, also those constraints are, for example, there's also the axion, which we think is probably going to be micro EV, but that's not a thermal relic. It's a different production mechanism, which would allow it to be cold. That I don't really understand very well, but it's apparently well understood by some. So, But we can also ask another question, which is, do we expect to see anything in this range? And in particular, yeah, there are some models of what are called hidden sector models. And in these models, you introduce some extra fermions. They have their own, let's say, U1 gauge symmetry. That's separate from our U1 gauge symmetry, which means that they have their own photon. So this would be like the primary vertex for dark matter particles that have some coupling constant, their own photon. And in a lot of these theories, you get terms that can give you a kinetic mixing between our photon, essentially, and the photon of this hidden sector. And under certain scenarios, then you can imagine that this whole thing here can be absorbed into sort of an effective vertex. And then at low energies, what this looks like is some dark matter has some tiny micro charge, electric charge. So there's been some papers on this. And in particular, they're probing dark matter masses. Here's a GeV down to the MeV scale. There's a big, wide range of parameter space open. Okay, and this is for one case where the mass of the propagator, or sorry, mass of the gauge boson is pretty high. If the gauge boson is very light, you get a different form factor. And again, very wide open parameter space. Now there's something you might see here. I noticed there's something I wrote in here called freeze in. Now the thing I said before about the WIMP Miracle, that production mechanism is called freeze out. You start with some particle that's in equilibrium, and sort of cartoony picture, and it drops out of equilibrium, freeze out. Okay. But you can ask, if this is sort of time in this axis, what happens in really early times? Really early times. Well, like during inflation, what's the number density of the particle in inflation? It's 0. So at some point after inflation, you get reheating, and then you have to build up to equilibrium before you can fall out of equilibrium. Well, I can imagine a type of particle that couples very feebly to the rest of the thermal bath. And instead of jumping up to the thermal equilibrium, it slowly grows in number density until at some point it doesn't even reach equilibrium, but the temperature of the universe becomes too cold to produce it. And what's happened is that this sector, these particles, started out essentially empty and was slowly populated, slowly, and then that population was left there, and it's a production mechanism known as freeze in. And this, to me, is compelling because it's another thermal production mechanism. You don't really have to specify much about the ultraviolet details of your theory. You can just say, okay, you have to specify something about how it couples to the bath and whatnot, but it's an interesting production mechanism. That's generic. Okay? And so that was, we'll go back here, this region here. For this particular type of dark matter candidate, this region in here will give you a candidate that can be produced with the right relic abundance by this freeze-in scenario. Okay, so you want to ask, how do we look for this stuff? And if you want to look for this stuff, remember with dark matter direct detection, we're looking for nuclear recoils. If I look at how much kinetic energy can a dark matter particle impart to a nucleus as a function of the dark matter mass, it drops off tremendously as you go up to smaller and smaller dark matter masses.
Even though as the dark matter mass goes down, its kinetic energy.
It's kinetic energy. We know the velocities, right? So they always are going to have an order 10 to the minus 3c. So
number density goes up.
Yeah, the number density will go up.
The number density goes up.
So the rate depending on
Yes, the constant energy density is the number we have.
But if I have 10,000 EV scale nuclear recoils per day, I still can't detect that. Okay, this is just because of the reduced mass of the. But if I do the same thing for electrons, the reduced mass isn't as much of a killer. And it turns out that this energy scale for electrons is the scale of atomic binding energies. So maybe something that we could exploit. Okay, so there's three theorists that looked at this, and they made a prediction for, this is the amount of energy that an outgoing electron that was kicked by a dark matter particle could have for different types of these sin sector things, one cross-section in different nuclei. So the color coding is for the nucleus, and then the dashed and the solid lines tell you the mass of the particle. And we're here, the type of the recoil energies we're looking at is in the order of, this is EV, so 1 EV, 10 EV, tens of EV, that scale. And that is possibly something that we can probe. And in fact, they did even further. They worked with them, and in a detector like Xenon 10, which was one of the predecessors of LUX, they made a prediction for a given cross-section, what would be the rates of 1 electron ionization events, 2 electron ionization events, 3 of electron ionization events as a function of dark matter mass. Okay? And remember I said, I made a big deal earlier on about the liquid Xenon TPC, that it has this really complicated ionization readout mechanism that is sensitive to single electron ionization signals. So it's something that, in principle, one can affect.
Is that cross-section typical for weak scale interaction?
It's not really dominated by weak scale because it's not really a weak process. It depends on
super weak charge.
Yeah, it's a combination of this G dark and this epsilon term, which is the kinetic mixing, and then some details about the mass of the gauge boson.
So you're combining all of that into one effective charge.
Yeah, I mean the
Right?
details of this give you a form factor as well. So we look at different cases for a massive one, for a light one. Okay, and there are some constraints also. For example, remember I talked about the bullet cluster. We know that dark matter is not collisional, or at least there's a degree to which it's not collisional, and that puts constraints on G dark.
Now, in this case, SM here is the electron, and it's
That's right.
interacting via, it looks like just a very weak version of electromagnetism.
That's right.
So there's a constraint on the mass of A also, right? A prime, based on galaxy formation and the range of the force. It cannot be too massive because then it will become a short. Sorry?
They're not thermal. Remember, they're not thermally produced. So I don't think you get much constraints from there. It's like axion is very light, much lighter than neutrino, yet it's not considered hot dark matter because it's not.
But if it's too massive, it will create a short range force.
If it's too massive and it has a short range force, then it could be problematic, but I don't think the forces you're coming here anywhere near. Anything is too problematic when it's too massive. It's relatively opposite.
Okay.
I guess if this was very light, if you look at propagation, long-term distance propagation of photons, you might start to see evidence of this vacuum dispersion. The mass of the photon. Let's go back to the blue, which was here. Right, so there was a published result of Xenon 10 that showed a spectrum of the very low energy ionization signals. And so we took this and we sort of analyzed it in this sense. And this is really interesting. Remember, I made this claim that we're sensitive to single ionization signals, and you can really see this quantization of the signal here.
Can do that too.
What's that?
LUX can do that too?
LUX can do that with some caveats that
Well, I mean, our plot looks way better than that, but the interpretation is complicated.
yeah. This is, it's quantized when you look at the electrons that leave the surface, but there's sometimes a difficulty in getting the electrons across the surface, from getting up to the surface. So if we have some model for calculating the rates of single, double, and triple electrons, and then we look in Xenon 10, which is one of the only results where we can actually look for this, in literature, we can put constraints on that and start to carve out regions and parameter space here. So we did that for this scenario where we have, I cut off the form factor, that's for the heavy mediator. Oh yeah, here we go. Heavy mediator, form factor of unity. For the same game, with light mediators, different form factor. Not quite touching the Friesen region, but what's interesting is that this is a very limited data set. This was only 15 kilogram days of data. And imagine something the scale of LUX or LZ, what we could do with that. And so this is done. These theorists, these are projected sensitivity curves for what you could do with a year of operation and a detector that is sensitive to single electron ionization signals. So the color coding is the nucleus, helium, argon, xenon, germanium. And you can kind of see that germanium sort of stands apart. And this is related to the fact that the band gap energy for germanium is so much lower than for these other nuclei. Okay. And I can play the same game for this space. A year of operation with a detector that has single electron sensitivity. Clearly throw this Friesen, this interesting Friesen.
Germanium has a smaller band gap than silicon.
That's right.
We want that.
That's right. Good. Germanium is essentially not good. But really, the killer here is that if I ask for a valence electron with germanium, what's the binding energy? It's about 4.5 eV. What's the band gap energy? It's about half eV. And the binding energy tells you about something about the kinetic energy of the electrons. So I said that the dark matter particles are moving at about 10 to the minus 3 C. The characteristic velocities of a valence electron is around 10 to the minus 2 C. A factor of 10 more over time. Okay. So, yeah. And so, to a large extent, what happens is not that the dark matter comes and smacks an electron, it's that the electron smacks the dark matter. And so, it's basically the excess kinetic energy of the electrons coupled with the fact that you don't need that much energy to overcome the band gap to observe the electron is what gives you this increased sensitivity of germanium. There's two form factors essentially. There's the nuclear form factor here, and the particle physics form factor here, and then there's an atomic form factor that needs to illustrate. But this is only true if you can build a detector that has single electron sensitivity, and that's never really been done in semiconductors like germanium. So the traditional method for reading out ionization as a transistor feedback setup doesn't really work. You can't get single electron sensitivity with that. And so instead you can think about physical amplification mechanisms. So for example, an avalanche photodiode or an avalanche diode is something that can detect single electrons. But that was tried by some Russians in the 90s, and they couldn't really get enough detector mass to really build anything interesting. There's also the CDMS approach. CDMS is another dark matter search. They have germanium detectors that are operated at about 10 millikelvin. Okay, and as the electrons travel through the germanium, they kick lattice points and they produce phonons, and you can detect those phonons. It's basically a multiplication of each electron produces many phonons, and you can detect those. And it's a really promising approach, but after decades of R&D, they still haven't been able to demonstrate single electron sensitivity. So we probably can do it in the future, but it's been a long time coming. So what we can do is think about, to our example of liquid xenon, we extract the electrons from the absorbent material. And if you extract the electrons, you can easily get single electron sensitivity. You can think about a photomultiplier tube. This is a situation where the absorber, think about the photocathode, the electrons are extracted, go through a dynode chain. You can easily see single electron ionization signals. Or the dual phase TPC, like I explained, you can easily get single electron sensitivity. Okay. And so one could ask, what would be possible if you could extract electrons from a semiconductor? Would you be able to get single electron sensitivity? And the answer should be yes, because it would be rather easy if I had something like silicon here, extracted the electrons. I could multiply these electrons with dinodes, like a photomultiplier tube, so PMT without the P, or a multi-channel plate, which is essentially something like a dino chain. These things can be used to get single electron sensitivity. But doesn't answer the question of how you would extract electrons from the surface of a semiconductor. And well, in Xenon, for example, this is a plot of the extraction efficiency of electrons as a function of the field above the liquid. So you have to apply an electric field to pull those electrons across the phase boundary. Okay. And in Xenon, you start to get close to 100% extraction efficiency at around 10 kilovolts per centimeter. Okay. But in something like germanium or silicon, you need a much larger field, possibly as high as 10 to the 5 kilovolts per centimeter. So much, much higher. But it turns out that if you do some tricks with the surface, you can produce really high fields. These are something called field emitter arrays. These are devices that were invented in Menlo Park in the 60s. They produce a microscopic array of tips and some gate electrodes that are very close. And these are very sharp, and they've been demonstrated to produce easily, in this case, about 10 to the 5 kilovolts per centimeter field densities with just a 30 volt difference between here and there. So like something in LUX, we have to deal with very high voltage components. This is a very low voltage application. So something that's been demonstrated. So you could think about how to build a detector out of this. Maybe have, so those of you who are not detector aficionados, generally when you build a semiconductor detector, you take one edge and you dope it, and you make a diode and reverse bias it, and then in this case the electrons would go up. These electrons, with an animation, they go up, they get extracted from these tips, and then you have some multiplier up top where you can see the electrons. And what's nice about this, you would also be able to get some sort of positioning here, because you could tell where these electrons came from in this way. So that's sort of a crazy idea, but lest you think this idea is crazy. I was talking with Charlie Hunt, who's a professor in the electrical engineering department here, and he said, oh, well, we built something like that once. And we built an X-ray imaging detector, and here the X-rays come in, get absorbed by some layer on silicon. With a tip array, the electrons are extracted and go into a microchannel plate. So it's been done in different applications. So
That's not a single.
well, the uncertainty would be in this process here, depending on like what's the efficiency you have. If I have n electrons in the bulk, how many of them get extracted into the thing? But the microchannel plates can easily detect single electrons.
But the photocathode conversion screen there
That's also
would have a dark current, wouldn't it?
I think that's not the case, because dark currents are usually coming from thermal excitations, and if your surface here is tuned so that X-rays are kicking off electrons, then thermal excitations are not going to be able to give you X-ray energy.
Oh, but fields.
Yeah, I'm not really sure what the fields they do, but you need not too high voltages here at least. Of course, you're going to have huge fields here, right? Because that's the idea for extracting electrons.
But the thing with the field emission points is reverse bias, right? And so there's a dark current inside it.
Oh, you're talking about like a leakage current.
Yeah.
Yeah. So that's true. You can control that a lot by the purity of this silicon. You can control it by the temperature as well, right?
So
Pulling it down to 77 Kelvin from room temperature, for example, gives you a huge reduction in that current. So.
Yeah, extremely pure silicon in the bulk region. Okay.
So I would say stay tuned. Okay, so I just want to summarize. Let's say 10 minutes long, which is not too bad for the first pass of this talk. Okay, so I told you about dark matter. It's important in the dynamics of galaxies, clusters, large-scale structure. I told you about the WIMP and how awesome the WIMP is, and how well motivated it is, and then I told you about how we're trying to detect it. But I also told you about what's wrong with the WIMP. It's not completely dead, but there are perhaps motivations to look at things besides the WIMP. And fortunately, even though we've been pursuing with the Xenon as a WIMP detector, it has it casts a very broad net. I'm sensitive to many other types of dark matter particles. So thanks for your question.
Are there more questions?
Very
Is
nice
everyone
talk.
tired and wants to go?
Very nice. We asked a lot during it, so we sort of used our best we can. I learned a lot.
Oh, good.